Can you hear me at the back? Good afternoon, everyone. My name is Jyoti Aneja, and together with Alex and Aditya, we were wondering, can CNNs do better for image captioning than LSTMs? Now, image captioning is an important and challenging task. In recent few years, significant improvement has been made in the area of generating relevant and accurate captions given an arbitrary image. The state of the art has been achieved by LSTM-based models, which are inherently recurrent. So my talk today will tell you about our completely convolutional approach that not only performs at par with the LSTM-based approaches, but also provides us insights on why CNNs could actually be better candidates when language vision tasks like image captioning are of interest. So what's the goal of image captioning? Given an image, like for example the one you see here, I want to generate a description of the image. For example, a hot dog with a pickle and a drink. This was generated by AI. Some possible applications could be improving our personal assistants, like the ones you see here, helping and supporting the disabled, or for more elaborate tasks like storytelling. So what's the task? Given an input image I, I'm interested in generating a sequence of words y1 to yn that describe this image. For example, a dog is looking out of the window of a car. Provided that I have a data set D with pairs of images and ground truth captions y star, where y stars are the words that are obtained from a vocabulary we. And my goal is to maximize the probability of producing a caption describing the image conditioned on the image. In other words, maximizing the probabilistic model PW with respect to the model parameters. Since the recent state of the art has been achieved by LSTM-based models, it's only fair that we begin by reviewing LSTM approaches. So let me first tell you about how inference or test time happens for an LSTM-based approach. So we input an image I through a deep net like VGG16 into the zeroth time step of LSTM through an image embedding. The hidden state from this time step, along with a vector representation of a start token through an input word embedding, is fed into the first time step of LSTM. At this time step, at the output, we obtain a distribution over the vocabulary words for the first word. And we take the max probability word and feed it into the next time step along with the first hidden state. This process continues until either we sample our end of sentence token as the max probability word, or we reach the previously decided maximum sentence length. During training, instead of providing the previously generated word at the next time step, we do something called as teacher forcing, where you provide your ground truth word at every time step. Now what's happening here? An inherent property of this method is that at every time step, my output word depends on the hidden state that's obtained from the previous time step. That makes this method inherently sequential. So what I'm going to, yes? So what I told you before, this is testing. During testing, whatever, it's sequential because the word you generate at the previous time step is what it goes at the next time step. So it's conditioned on the previous word generated, whereas during training, it's conditioned on the ground truth word, previous ground truth word. So at the top here, you see it's the probability of generating the next ground truth word, y2 star. Yeah, it's optional.
So, I mean, then you have perfect agreement between training and testing regimes.
Yeah.
Right.
Okay, so let me tell you about our convolutional approach. Now, if you look at this diagram, most of it looks very similar in architecture to the LSTM-based approach. We still have the image that's being fed through a deep net. We still have these input word embeddings, and we also have the same output word embeddings. So what's different? The LSTM cell has now been replaced by a masked convolution, by masked convolutions. What are these masked convolutions? So these masked convolutions are basically 1D kernels that have been masked in such a way that no word ever sees the future words. And it only sees a set of past words, and the width of these convolutional kernels makes us determine how much in the past do we want to see. Now, since there is no inherent hidden state involved here, I can carry out the scanning of these kernels in parallel over the entire sentence, and hence I get rid of the sequential property of LSTMs, and the whole process is now parallel. So what did we discuss? We saw that the training is parallel in case of CNN-based approach, unlike for LSTM, which leads to an improvement in the training time per parameter. In this table here, I show you a comparison in the number of parameters for both these models, and also some analysis of the training time. So we see that in case of CNN, for almost 1.5 times the number of parameters, it has nearly the same training time per epoch, or it has much less training time per epoch per number of parameters. Yeah.
This kernel is a fixed window length, right?
Yeah, we chose it to, you choose it to be a fixed window length depending on how much in the past you want to load.
So whereas an RNN-based procedure can potentially capture a long-term dependency.
Yeah, so in this case, to capture the long-term dependency, like the dependency of the first one and the last word, you replicate the same layer, same convolutional layer over many times. So this one, if I have my convolution kernel of size 5, it's only going to look at 5 in the past. Right. But if I replicate this over several layers, then as a combination, my field of view keeps increasing. So it's able to see the whole sentence. Yeah.
One more question.
Yeah.
The convolutional kernels, you're showing 3 of them here. Those are all the same parameters, just with different masks?
Yes.
Okay.
It's just showing that it's getting slid over the whole sentence. Okay, during inference, we are still parallel, just like LSTMs. Now, one would wonder, how well does a model like this work? In this plot here, I show you the cross-entropy loss values for both CNN, which is in blue, and LSTM in red, over the total number of epochs. Now we see that CNNs actually have a worse or a higher cross-entropy loss value. Well, but surprisingly, when we look at the standard metrics for image captioning, like blue, which measures the n-gram precision, Meteor, that actually looks at the explicit word-to-word matches, Rouge, which is a recall-based method, and CIDR, that measures the similarity between the ground truth and the generated sentence, depending on the notions of grammaticality, saliency, precision, and recall. We see that the CNN model performs at least as good as the standard conventional LSTM, if not better. Now, what does this show? To investigate this further, we looked at how much is the entropy in the captions that these two models are generating. So what do I mean by this? At every time step, we are actually outputting a distribution over our vocabulary. If this distribution is more or less uniform, then we would call it a high entropy distribution. That basically means that your model is not very sure of what it's predicting. If the model is really sure of what it's predicting, your distribution will be peaky, or we can call it a low entropy distribution. So in my next plot here, I show you the entropy over the words on the y-axis versus the total number of epochs on the x-axis. The blue again is CNN, and the red is LSTM. We see that the CNN has a higher entropy compared to the LSTM. What would it mean? Well, CNNs definitely are not sure of their predictions as much as LSTMs are. And that's probably what is getting reflected in the bad or in the higher negative log likelihood. Well, but the metrics seem to be telling a different story. CNNs are performing as good as LSTMs. So to investigate it further, we looked at the word accuracy predictions. Here on the y-axis, we have the percentage of times CNNs predicted the correct word versus the LSTM over the total number of epochs. Now we see that CNNs actually do as well as LSTMs on the val set, and even better than LSTMs on the trained set. So what does it mean? CNNs have high entropy captions. They're not sure about they're not as confident about what they're predicting, but they still make the right decision. That means if I had an option to predict a car somewhere, CNN is giving still a slightly high probability to something like a truck, but it's able to predict that it's a car. Well, in that case, we would see that high entropy is actually an added bonus, because for tasks like image captioning, diversity is also of interest. In this next plot here, I show you the number of unique tokens that these both models produce over over the word locations in my sentence. The blue is CNN and the red is LSTM. We see that the blue CNN consistently produces 50 or more unique words at every sentence location for most of the locations as compared to LSTMs, while clearly indicating that CNNs are willing to produce more diverse captions. Additionally, in this graph, on the y-axis, I show you the norm of the gradient at the output classifier layer for both these models and the input word embedding layer over the total number of epochs. We see that the blue CNN at the output classifier layer, which is the solid line, and the dotted line is the input word embedding layer, there's much less decline in the gradient norm. Whereas for LSTM case, the gradient norm has dropped to a big amount. It clearly shows that CNNs are not suffering from vanishing gradient problems as much as LSTMs are, well indicating that if we have more data or bigger data sets, CNNs might continue to learn, whereas learning might stall for LSTMs. Lastly, I would like to show you some captions that are generated by these two methods versus the ground truth. Let's look at some of them. So for example, let's look at this one. So the LSTM says it's a living room with a couch and a TV. CNN says it's a living room with a couch, chair, and television. And the ground truth was a living room filled with a living room, furniture, and decor. It's pretty good sentences. Another one, let's look at another one. LSTM says a street sign on a pole with a street sign. CNN says a street sign with a green light on it. And ground truth was a green sign on a pole with a street light. Well, pretty consistent. It's evident that both of these models are producing similar quality sentences, and which was also captured by the metrics. To conclude, we saw that convolutional approach to image captioning performs at least as par as the LSTM-based approach. It's faster to train, and it's trivial to parallelize. It doesn't suffer from vanishing gradients as much as CNNs do, and it's willing to produce more diverse words. And it's enough reason for us to look at CNNs if language vision tasks are of interest. Thank you.
Thank you so much, Jyoti. That was very nice and interesting. Are there any questions?
It's okay. I can just
So that it's recorded.
Oh, okay, right. Hi. So to me, it sounds like the LSTMs are producing great talk. They're producing uncalibrated predictions, which means they're more confident than they should be that the probability is blah blah blah. So have you looked at maybe calibration plots of like the probability predicted by the LSTM versus the actual probability that it's correct? Because I suspect the LSTM will just turn out to be overconfident, and that's why it's getting better cross entropy, because that rewards confidence, but actually not an improvement in accuracy.
So what do you mean by looking at the calibration?
Oh, so calibration is like if you look at cases where the LSTM says that there's an 80% probability that this thing is this word, and you look at how often it's correct, is it actually correct 80% of the time, or is it correct only 30% of the time?
Yeah, it's correct lesser times. That's why the CNN has a higher accuracy.
Yeah. So like that's called So
Okay.
another word for that is miscalibration. So yeah, it's totally consistent, and that's a good thing for CNN. So they're more calibrated.
More questions?
So I guess it doesn't really apply in the context of image captioning, but like in general for language tasks, people also use bidirectional LSTMs.
Right.
So that really breaks that sequential dependency to the past that you talk about in your motivation.
But it's still sequential for both the...
Yes, but then like it's not just dependent on the history like that on the words. It's not conditioned only on the words that you have encountered in the past, right? So, I mean, did you have a comparison with the...
So in that case, you actually apply it on the reverse sentence. Right. So that's also one of the ways. We haven't yet tried a bidirectional CNN analog, but that's something that might be interesting to look at.
More questions?
So this reminds me of the work of Facebook AI research on CNN for language models. But then there's a follow-up paper by Google saying attention is all you need. So it's interesting whether the same applies to your case. Like if you use attention with feed-forward networks, do you get the same result as CNN as well?
So in this work, we actually, so what I presented was only half part of the work. So what we have some experiments in which we have used spatial attention in addition from confi features of VGG16. But we haven't done it using feed-forward. So another interesting thing that one could do is perform the whole thing using a feed-forward network and see how well it behaves. We haven't done that, but yeah, I know of the Google paper and Facebook paper that actually came around the same time and kind of say the same thing on machine translation. It doesn't seem like that attention is all you need because our scores improve slightly when we have attention, but they do improve. It will be interesting to see what do feed-forward networks do for this task if we just remove the convolutions.
So are there any other questions?
I may have missed this. So in the LSTM, the information about the original image is kind of like preserved in the hidden state, and that's how like subsequent words are generated. So how is information about the original image kind of preserved in the CNN? Because there's no hidden state, so I was a bit confused about that.
So for LSTM, you input your image at the first time step. You're right, it's preserved at the hidden state. For CNN-based models, we actually input the image also at the initial time step.
Okay.
So you add your image to each of your word embeddings.
Okay, great. Makes sense.
More questions?
It could, because the image is actually, so the first word is really, really dependent on what the image is. It only saw the image features, but the subsequent words saw the image features through the other words in its state. It could probably change things.